Okay, working. Yeah. Let's get started. So I guess the plan now is we will have not this one. Sorry. Our plan now is we'll have our final next week. So final is next Monday, and so we'll actually try to we'll try to finish everything. If we really cannot finish, then I guess we will need to teach the rest of it on Thursday. But plan now is we try to finish everything today and have a final review on Thursday. And I guess we are also we already done our homework. But for the thing we talked today, then we'll probably release some questions with answers, so you can practice yourself for your final. Okay. And so we're a bit tight on schedule, so let's get started. So causality for Z transform. How do we see? I guess, but before we start, very quickly, do people have questions about everything we told so far? I think we have the properties of Z transform next time. Okay, so if we are good, then let's start with causality. So causality for Z transform, just like Laplace transform, we can see the causality from the ROC. Okay? And but it's a bit nicer than Laplace transform, where Laplace transform we say for usual function we cannot just see from ROC its causality. But Z transform we can, because so once again right-sided function give you this all-sided ROC, and the all-sided ROC only give you right-sided function, and then you don't know whether it's just right-sided function or it's causal. Okay, so now we are just abusing a notation, say h of n is causal, means that it is 0 for n less than 0. Okay, and but we have this property 4.5. It says that if your signal is causal, then your RC will also include infinity. Okay, so basically you have one or two conditions together, then you can determine your system is causal. That is, your RC need to include infinity. And this kind of also imply your RC is almost 1. Okay. And anyway, the rule here is that the system is causal if RC is the almost RC and also include infinity. Okay. So yeah, and then we can go back to, so this is our rule for causality is causal if your RC include infinity. Then we can back to rational function, then we can do a bit of more derivation. Okay? So for rational function to be causal, then once again your RC need to be the almost RC, and then this including infinity, you can express this including infinity in terms of the degrees of your numerator and the degrees of denominator. Because your RC include infinity means that when z goes to infinity, your h of z is finite. So that means that your n of z cannot grow faster than your d of z, and that just means that the power here cannot be more than the power here. Okay. So for rational function, you can judge whether it's causal easily by looking at the difference between those powers. So the power here should be, the uppercase power should be not greater than the lowercase power, because you want h of z to be finite when z go to infinity. And so let's see a quick example. And so here is our system function, and you are going to see the whole bunch of time. So h of z equal to this 1 over 1 minus 1 over 2 z minus 1 plus 1 over 1 minus 2 z minus 1, and with RC being outside z greater than 2, and whether the system is causal. Okay, so I guess let's do the voting really quickly. So I think this is causal, raise your hand. And think a little. Doing calculation what happens when z go to infinity. This is the causal, raise your hand. Okay, some people, and this is not causal, raise your hand. Okay, and indeed this is causal, and because first we check out the RC is almost pole, And when z goes to infinity, okay, so here we have the harder calculation. So you multiply everything out and actually express it as the rational function of z, then it's z squared over z squared. It's quite hard to calculate. But I guess there is some trick you can do here, so you can just take z to infinity, then the minus 1 will go to 0, so this is 1 over 1 plus 1 over 1, so this is 2. Okay, so 2 is finite, and same as this 2 here. Okay, so this is causal system, and another way you can do this calculation is you can just do inversely transform, because we already do the partial fraction expansion here, so this is 1 over 1 minus a z minus 1, and the inverse transform to this a to the n and a to the n, and so we have a pole at 1 over 2, a pole at 2, so this is outside of both poles, and actually they both inversely transform to this causal signal. Okay, so this is causal, and then we jump very fast to stability. Okay. And now stable is simpler, so just like Laplace transform. The system is stable if only if the RC includes this unit circle. So this is basically the same condition as Laplace transform, just a different geometry. So in Laplace transform, it was including the j omega axis. Now it's wrapping this j omega axis around here. It's including this unit circle. Okay, and then let's go back to this question. Okay. This thing, so we know it's causal now, and now we ask you, is this stable? Okay, if you think it's stable, raise your hand. So this should be very fast calculation. And if you think it's not stable, raise your hand. Okay. Yeah, it's not stable because it's z greater than 2. Then z greater than 2 does not include is z equal to 1. And also we just see it's inversely transforms. It's impulse response. It is 1 over 2 to the n and the 2 to the n u of n, and the 2 to the n u of n is an exponential ingrowing function, so it's very divergent, and this is not stable. You don't have convergent Fourier transform because this is an exponential ingrowing function. Okay, and now we go to different flavor of this question. Okay, and so the same system function, and now change the RC. RC is between two poles between 1 over 2 and 2, and it is causal and or stable. Okay, if you think it's causal, raise your hand. If you think it's not causal, raise your hand. Okay, and if you think it's stable, raise your hand. If you think it's not stable, raise your hand. Okay. And yeah, so I guess we are pretty good at this. So it's stable because now this is including the z equal to 1. Here we have a small sketch here, so between RC between this 1 over 2 and 2, and that's including this z equal to 1. And it's also not causal because we don't have the almost RC. And we can also check the both property from the inversely transform. So now this RC is outside of the first pole and inside the second pole. So for the first pole, we get this right-sided signal, right-sided inverse, and for the second friction, we get this left-sided inverse. So if you plot the function, you kind of look at this. It has this decay to exponential decay to n to infinity, and also this part is exponential decay to n to negative infinity. And so this is absolutely summable, but it's not causal because you have this n less than 0 part. That's a non-negative. And finally, we have this less ROC that's inside everything. And once again, if you think this is causal, raise your hand. And not causal, raise your hand. And I think this is stable, raise your hand. And not stable, raise your hand. Okay, yeah, and yeah, we got this all correct. So now this is not causal and not stable. So yeah, and we have the inverse transform here, and you see that this is all on left hand side. So this is actually called anti-causal, but anyway, this is not causal and also not stable because this 1 over 2 to n and go to infinity will be exponential growing. Okay. And we can, similar to Laplace transform, kind of combine all the things we know together. So now if we want to satisfy all three conditions, so if we want to have a causal or linear system that's also rational and also stable, then we need to have some, then all the poles of this H of Z need to lie inside a unit circle that have this particular distribution. Because you want the almost ROC to also include a unit circle, then all the poles must be inside this unit circle. This is similar to a Laplace transform case where you want all the poles to be left of your J omega axis. Okay, and I think we are pretty good at this, so let's see a bit more examples. So here we have a second order system. Whatever this means, it has a system function looking like this. Okay, 1 over 1 minus 2 r cosine z minus 1 plus r squared z minus 2. So this is a second order function for z minus 1 on the denominator. Okay, and so it has a pole at r equal j theta and r equal minus j theta. This is just a result. And here we say assuming causality is this stable. Okay, so here we do the calculation we want to do for you here. Okay, so this is exactly this thing checking. So yeah, so we have 2 poles here, and now we have a rational function of z and assuming causality, and as you is a system stable. Okay, so the people think this is stable. Think it's stable, raise your hand. Not stable, raise your hand. Maybe, raise your hand. Yeah, I guess this is a trick question, so I'll just say the result. Yeah, so this is a trick question because so the condition we have is we want all the poles to be inside a unit circle, but here we still have some undetermined thing here. So we our poles are at r equal j theta and r equal minus j theta. And where all that is inside unit circle is dependent on r. Okay, so yeah, so for r less than 1, everything is inside unit circle and is stable. For r greater than 1, it's outside unit circle and it's not stable. So like this. So we have a point here or a point here, and if r is less than 1, it's stable, and r greater than 1, then it's not stable. Okay. And I guess that's a very quick quick description about causality and stability. And now let's go to the next topic, that is linear constant coefficient difference equation. Okay, so let's see how we can use the transform to solve the difference equation. For example, I have a difference equation here, so y minus 1 over 2 y of n minus 1 equal to x of n plus 1 over 3 x of n minus 1. Okay. And so as we always do, when we want to solve those difference equation, we just apply transform on both sides. So apply the transform on both sides. And the property we need to use is this time shifting property. So x of n minus n0 will z transform to z to the minus n0 x of z. So y become big Y, y become big Y, and this minus 1 becomes this z minus 1. And x become big X, x become big X, and this minus 1 also becomes z minus 1. And then we can group things together, and let's keep this equation. What we want is what's big H. So big H is big Y divided by big Z, and you move things around, you see that it will be a rational function of Z minus 1 or a rational function of Z. And it's a bit nicer, sometimes it's a bit nicer to write it as a rational function of H of Z minus 1, because as we know that when we do inverse Z transform, this kind of term is nicer. But anyway, this is our H of Z. So H of Z is 1 plus 1 over 3 Z minus 1 over 1 minus 1 over 2 Z minus 1. Okay. And just like Laplace transform, we see that the equation part only gives us the algebraic part of H of Z. So these don't actually totally determine the system function, because we still did the ROC, and this is very reasonable because the difference equation itself doesn't determine the system. We still need some auxiliary condition, and so for example, if we say our system is causal, then you know your ROC must be outside of almost pole, etc. Okay, and anyway, so for this system now, there can be two different ROC because there is one pole and 1/2. Okay. And so if you are from our condition, you decide your ROC is outside ROC, then you will get a right-sided signal, right-sided impulse response for your system. And otherwise, if you have you determine your ROC is inside ROC, then you will have a left-sided impulse response. Okay. Okay. And now we try to do this inversely transform with different ROC. So first, if your ROC is outside ROC, then theoretically you need to do partial fraction expansion on this thing in terms of maybe power of z minus 1. But here we show that it can be a bit easier, okay? Because once again we have this very nice time shifting property. We already use this when we talk about property, and we'll see this again. Okay, so you see that the upper power here is 1 plus 1/3 minus 1. We can just say is this thing multiplying with this partial fraction that we already know how to do inversely transform. Okay, and for this extra part, we actually don't need to do expansion. So I guess the standard way in terms of Laplace transform would say you need to divide this thing with this thing and to get rid of this z minus 1 power, etc. But we see that there is an easier way to get rid of this z minus 1 power is you just say, well, we do linearity and to break those two terms. And for this z minus 1 power, we just use time shifting property to correct it. Okay. So we say you get this extra z minus 1 power just by getting this extra time shift. Okay. So the z minus 1 just give you this. So without this z minus 1, this factor transform to this 1/2 to n u of n. And with this extra z minus 1 power here, then by the time shifting property, you just change every n to n minus 1 because this was x of n minus 1. So this is n to n minus 1, n to n minus 1. And this is a much easier calculation than going to long division to get rid of it, etc. Okay, so here we have a trick to so we have this rational function of z minus 1, and for the numerator you can just get rid of every term here by using a time shifting property. Okay, and similarly we can do this for inverse the transform for z less than 1/2. Okay, and once again, so the first term is the same. So first term we change inversely transform to a left-sided signal, and this is minus a to the n u of minus n minus 1. And then the second term, once again you do time shifting property, and so every n change to n minus 1. So this n go to n minus 1, and this minus n minus 1 you need to change it to minus n minus 1 parenthesis minus 1. And so you do the calculation here, you see that this is minus n. Okay, so this is a much simpler calculation by using the time shifting property. Okay, and anyway, and we can check it up this, and that the system, this impulse response will be anti-causal and unstable. And that check out with the ROC we have. ROC was less than 1/2, and so this doesn't include unit circle, so it's unstable, and also it's not almost ROC, so it is not causal. Okay, and we have a general form. General form of our algebraic part of system function by just looking at the difference equation. So if we have some ak y over m minus k equal to some bk x over m minus k, then our h of z is y of z divided by x of z. So the coefficient of y of z is down here, coefficient for x of z is up here. You have the summation bk z to the minus k over summation ak z to the minus k. So you can kind of just look at the equation and write down the algebraic part of h of z. And then the RC you need to determine by other conditions. Okay, so let's see more example of this. Say we have two pieces of information and we want to determine the system function. And the first information is, I guess both of information is an input-output pair. So first is x of n is this exponential decay function, and y of n is this two part of exponential decay function. Then second one is weirder, so x of n is minus 1 to the n, then y of n, this output will be 7 over 4 minus 1 to the n. Okay. And then the first property, so the first hint is a bit easier to use because you can do z transform on both of them. So you z transform on this x1, and this is our favorite signal, and they will z transform to 1 over 1 minus a, z minus 1. A is 1 over 6. And RC is outside because this is right-sided. And so this is our x1, and then we also have our y1, and it's just a linear combination of two of those exponential functions. So it just z transform to this thing. But now this is a bit annoying because we have some unknown in our y. So we have a being an unknown here, that's just a real number. Anyway, we can write down y as a function of a, and we express it as a rational function of z minus 1, will look like this. Yeah, so we have this a plus 10, that's 5a over 3, etc. Okay, so from this y1 of z, big y1 of z, and the big x1 of z, we can get the algebraic part of our system function is big y1 divided by big x1. And yeah, you see it's this very complicated function. Okay, so this part is y1, and then this extra part is x1. Okay. Excuse me. And we can also think about the RC of h will be so RC of y need to be the intersection of RC of RC over h and x, and I guess for now we don't need to determine RC, and so I'll skip that. And then for the second condition, it's harder. Okay, second condition is harder because those two signals don't have convergent z transform, because this minus 1 to n is just two convergent everywhere. And but just like those, we have seen similar question in Laplace transform. And for this signal, we need to remember that for those signals, we need to remember that the system function is also the eigenvalue of is also the eigenvalue for this eigenfunction z to the n. And we see that this x2 of n is exactly in form of z to the n with z equal to minus 1. Okay. And so we see that this y2 of n equal to 7 over 4 minus 1 to the n is exactly this eigenfunction equation with h of z equal to 7 over 4 and x of n equal to minus 1 to the n. Okay. And so we know this 7 over 4 is h of z with z equal to this minus 1. Okay. So this is important equation here. So y2 of n equal to 7 over 4 minus 1 to n equal to minus 1 to n h of minus 1. And so we know that h of minus 1 equal to 7 over 4. Okay. h of 1 minus 1 equal to 7 over 4, and from here we can solve for a, because we have this complicated expression for h of z as a function of a, and we now get 1 point of h of z, and so we plug in this minus 1 into h, and we can solve for a, because now this is just a linear function of a and equal to 7 over 4. And with all the algebra done correctly, we will see a equal to minus 9, and we have our h of z equal to this thing. Okay. And we can clean up our h of z here, and we see that h of z has two poles, has a pole at 1 over 2 and 1 over 3. Okay, and finally, now we want to determine RC. Okay. The RC is a bit annoying, okay, because it's a bit convoluted logic. So although we can probably guess that the RC is outside, because x1 and y1 RC being both outside. But if we want to do it carefully, and we need to analyze all the possibilities. So there are two poles for h of z, as we say, is this 1 over 2 and the two poles should be this 1 over 2 and 1 over 3. Let me see. Its two poles is 1 over 2 and 1 over 3, and so h of z has 3 parts of RC, outside 1 over 2, between 1 over 2 and 1 over 3, and inside 1 over 3. And then there are RC for x1 and y1. RC for x1 is outside is 1 over 6, and RC for y1 is outside is 1 over 2. And what we know is the RC for y1 must be containing at least intersection between RC of h and RC of x. Okay, and okay, and so you see that if you pick those two inside RC, so this is inside RC, this is less than 1 over 3, or between 1 over 3 and 1 over 2, and consider the intersection with x1, you see the intersection all have something less than 1 over 2, and that's not possible. So the RC for h must be the outside RC, must be the greater than 1 over 2. Okay. And finally, we can determine some property of the system. Now we already know the system function. So system function has this form, and with RC being greater than 1 over 2. And so first we see that RC include unit circle. So once again, the system is stable. And for causality, we see that we have the almost RC. For causality, we see that we have the almost RC. Also, h of z, as z go to infinity, is a finite value, so it includes infinity. So the system is also causal. Okay. And now we know the system is causal. We can also express this system as linear. We can also express the system as linear constant difference equation. So just from this system function expressed as a rational function of z minus 1, you can write down the system function here. So those corresponding, the numerator corresponding to terms of x. So this 1 becomes x, so this 1 over 13 over 6, and z minus 1 becomes x over n minus 1, etc. And lowercase corresponding to terms of y. And finally, this causal condition means that you can just think the system satisfy the condition of initial rest. Okay, so from those two conditions, we derive the whole system function and determine its property, and also write down difference equation that will give you this system. Okay, so this difference equation with condition of initial rates will give us this system. Okay. Okay, then let's see next example. Okay, so now is a very complicated example. It's actually a lot of true or false. Okay, so we have a stable and a causal system with impulse response h and rational system function big H. Yeah, and we'll assume that we know big H contain a pole at z equal to a pole at z equal to 1/2. So we draw a picture here. So we will pole at 1/2 and 0 somewhere on unit circle. We don't really know. Okay, 0 somewhere. Yeah. And there might be other pole 0. So we just say there is a pole here and 0 somewhere on unit circle. And now now we want to do this true false or maybe question many of the condition. Okay, and okay, so we have a whole bunch of them: A, B, C, D, E, F, A, B, C, D, E. Okay, so 5 of them. Okay, and let's see, try to do this one by one. So first is f of 1/2 to the n, h of n converge. And if you think this is true, raise your hand. If you think this is false, raise your hand. People doing calculation. Okay. And if you think this is maybe, raise your hand. Okay. Look like this. And I think this is false because we actually give a condition for this, and this pole at z equal to 1/2. Okay, and because this Fourier transform of 1/2 to n h of n corresponding to z transform at sorry, I actually get it wrong. So this is true. Here Fourier transform of 1/2 to n h of n corresponding to z transform at z equal to 2. Okay. Oh, okay. And okay, yeah, and so we have this condition. So this 1/2 to n corresponding to z equal to 2 because this is 2 to the minus n. This 1/2 to the n is 2 to the minus n. Okay, and we have a pole at 1/2, but we also say we don't really. We also say that the system is stable and causal. Okay? And from stable and causal, we know that so this is a rational, stable, and causal. So we know all the poles must be inside unit circle. And so there is no pole outside of unit circle, and RC including everything outside this unit circle. And so this z equal to 2 is inside RC, and yeah, and so z equal to 2 is stable, is convergent inside RC. And hopefully we don't people don't see the answer for next question, but is h of e to a j omega equal to 0 for some omega. You think it's true? Raise your hand. Okay. And you think it's not true? Raise your hand. False. And you think it's insufficient? Raise your hand. Okay. And the answer is indeed true. Okay. Because h of j omega is just e to a j omega is just this system function big H on this unit circle, and we say there is a 0 on unit circle, so that's the point where big H of e to a j omega equal to 0. Yeah. And next one is h of n has finite duration. So this time domain signal has a finite duration. You think it's true, raise your hand. You think it's false, raise your hand. You think it's maybe, raise your hand. People need to think. I guess let's think a little more. People want to answer again. True? False? Maybe? Okay, I think it's false, yeah. Because you have finite duration, then RC is entire Z plane, and or infinity and 0. Okay. And but if you are in entire Z plane, then then you cannot have a point Z equal to 1 over 2. Okay. So it's not a finite duration. And next one is H of n real. If we think it's true, raise your hand. False, raise your hand. Maybe raise your hand. Okay. I think this one maybe. Let's see. Yeah, it's maybe. So there is really no condition about this. It's if you want it's real, then what we say is the point zeros come in pairs. But we just say there is some pole here, some zero here, but we don't really know where they come in pairs. Okay, and the next one is let's see, G of n equal to n times H of n convoluted with H of n is the impulse response of a stable system. Oh, this is very complicated. I don't think we can do calculation, but we can take a guess. I think it's true, raise your hand. False, raise your hand. Maybe raise your hand. Let's see for the answer. Okay. Okay, this one is true, but I think this requires a lot of calculation, so yeah. Okay. Okay, let's see how we do. Okay, so system is causal, so H of n equals 0 for n less than 0. Okay, and okay, what's our question? Want this into this table. Okay, so how this goes? Okay, so H of n equals 0 for n less than 0, then H of n convoluted with H of n. Okay, so H of n convoluted with H of n is still causal. Okay, and G is still causal. Okay. Convolution property. Let's see. The system function corresponding to the impulse response. So you have H convoluted with H, then into the Z domain is a big H square. And yeah, we need to use a whole bunch of property to see what's the Z transform of this n times the H convoluted with H. So H convoluted with H is a bit easier than Z transform is just a big H square. And then we use the differential property to get the HRN here. Okay. So differential property says that you want nx of n, then you need to do minus z and d big X dz. And so this is pretty hard to do calculation. So you have minus z here, and then our small x and the big X is actually H convoluted with H and the big H square. So we need to do ddz big H square. So this is minus 2z and H times dh dz. Okay. And okay, so we just see where are the poles of those things. Okay. And so we know it's all causal. Okay, so this is actually pretty hard calculation. So first we determine that this system is causal, and now we need to see whether all the poles are inside unit circle. Sorry, let me change this a little bit. Okay. Now we need to determine whether whether all the poles are inside unit circle, and we see its algebraic form is these three things multiplying together. It's z and h of z and ddz h of z. Okay. And we see before that ddz has dhdz has the same location of poles. Okay, because differentiation don't remove poles. Okay. And then you multiplying two things together, you also don't remove poles, so it's still same location of the poles. And finally, you multiply with this z, and z is 0 at z equal to 0. And so at most you can do is you remove remove a pole at 0. Okay. And so basically h of z has okay. So the pole location of G compared to H is every pole of H except maybe a pole removing at the origin. And but the H of Z has poles all inside unit circle because because it is stable and causal and rational. And so this H of Z is still has poles inside unit circle. Sorry, G of Z also has poles all inside unit circle. Okay. And I guess we also need to say it's still rational because Z is rational, H is rational, and dHdZ is still rational. Okay. So G of Z is stable causal rational and having poles all inside unit circle. And it's a causal and rational, and all poles inside unit circle, so it's stable. Okay. So it's a very long argument. It's stable. Okay. Any questions so far? Hello. Okay, and we have our battery bank. Okay. Yeah, so the next one you need to do very long calculation. Yeah, and this is reasoning. Okay, and next, let's see, we have about 5 minutes. I will skip the talking about the system, some special system here. I guess we can say very quickly, so it will be on slide, but I guess not on final. But here we have open system as the Z transform, and you still want very quickly. You still want your point 0 in these conjugate pairs. So if you pole here, then you need to have a symmetric 0 around unit circle. And by symmetric means that you have a pole at BK, then you need to have a 0 at 1 over BK star. And you can verify yourself through the algebra here. You have this pole 0 pair, then for every Z on unit circle, the absolute value of your big H will be 1. Okay, so this is the pole 0 system. Open system, and then you have other system, etc. Okay, and let's go to the next topic we want to talk about today. That's the block diagram. So block diagram will be quite similar to the Laplace transform block diagram, but a bit different because I guess it's actually a bit easier. So so be a spoiler, the easier part was that in Laplace transform, we avoid using differentiator because we say differentiation is very unstable. But kind of corresponding to differentiator in discrete time is just a unit time delay. And unit time delay is actually very easy to do, just input your signal later. And so we can use a lot of unit time delay. We don't need to use the accumulator, and that makes things a little easier. And anyway, here is a part that's exactly same as the Laplace transform. So if we control the feedback loop, so we'll control everything based on this, almost everything based on this. So you have a feedback loop like this with H1 here and H2 here. Then you can calculate that this feedback loop is equivalent system function will be this H1 over 1 plus H1 times H2. And yeah, so this is the algebraic part of the system function. And as in Laplace transform, we kind of ignore the RC part. We just talk about how to control the algebraic part. And and just like in chapter 9, be careful with our weird notation. We have a minus sign here. And here is a small review of the same equation on chapter 9. So this was H of S, now it's H of Z. Okay? And the calculation is exactly the same, so we don't repeat it. Okay? And now let's see a bit of example. So we have a system function like this. This is one of our favorite system function. 1 over 1 minus 1 over 4 z minus 1. And so from the thing we just talked about, we know that it corresponds to it can be correspond to a difference function like this. So this is 1 minus 1 over 4 becomes this y of n minus 1 over y, and y of and the z minus 1 become y of n minus 1. And this is equal to x of n. Okay, and then you just look at this equation. Just look at this equation. Then you can construct a block diagram for this equation with this block diagram. So x of n, y of n. So x of n equal to y of n. Yeah, so here we have our equation. So x of n equal to y of n. Then, sorry, I think there is a bit of type. Oh no, okay. So x of n equal to y of n, but minus minus 1 for y of n minus 1. Okay, it's a better equation here. So is that let's do a calculation here. So what we have is y of n equal to x of n plus 1 over 4 y of n minus 1. Okay, so here this line is y of n and equal to x of n plus this y go to z minus 1, which is unit time delay, is changed to y minus 1, and then you have y over 4 here. Okay, and yeah, so we need to talk about this z of minus 1. So z minus 1 means system function of a unit time delay, as we say. And I guess this is z minus 1 because this is actually we are writing in the z domain. Okay, and so this is the time delay relation we keep using. That's very useful for the transform. So remember, x of n minus n0 will the transform to the minus n0 and big X of z. Okay, so that tells us that if you multiply by z to the minus 1 on the z domain, then on the time domain you will change from x of n to x of n minus 1. Okay, so that's why we say it's z of minus 1. Okay, and as we said, so the output is w of n here will be y of n minus 1 because of this time shifting property. Okay. And anyway, so this is system function. We see that it can be done by this feedback loop. And this feedback loop is actually same as the feedback loop we just talked about. So we have this more general H1, H2 thing. And so if we just combine this z minus 1 and 1 over 4, and also fix this minus sign with the H1 minus sign here, then we see that we have the form of feedback loop that we just talked about. This figure 10.18. Okay. So this is same as this thing with just h1 equal to 1 and h2 equal to this minus 1 over 4 z minus 1. Okay. So h1 equal to 1, h2 equal to minus 1 over 4 z minus 1. And we can see that this also check out, because if we plug in those h1 and h2 equal to this equation, then we'll get back to this equation. Okay. And yeah, so we have exactly time to break, and we'll talk a little more about block diagram next class, and we'll finish with unilateral Z transform. Okay. Okay, so see you in 10 minutes.
就是他不知道怎么转转，然后他会飞起来，然后人撞中的时候，他这一路飞到外面去，这个很明显这不是我问题。
他动力出错了吗？
没有啊，动力只是他这种撞，我不知道为什么他地板会看成，就是他会原本在比方说突然高一格线，然后就开始上就开始那个
跳，
后来那个手的问题。
还是输吗？就把你的测试机制去接过。
我没有测试哦，我就觉得就是。
那你就随意再换一个。
你可以直接跟他。
没有啊，你那 level 2也好嘛，就两个都跑好了，可以，还有会。
我觉得他只手到。
你那个方法是打得好，我给你选了，两个时间。比较多自保护。
Hello. Okay, let's get back to blood diagram for the transform. Okay. so we see our basic block diagram for Z transform. We see that for this difference equation, this y over minus 1 over y of minus 1 equal to x over. We can use a block diagram like this one or this one to get this difference equation, and you will have the system function that's h of z equal to 1 over 1 minus 1 over z of minus 1. Z to the minus 1. Okay? And let's see a more complicated system function and how we can express this as a block diagram. So we have h of z, once again as a rational function of z minus 1. H of z equal to 1 minus 2 z minus 1 over 1 minus 1 over 4 z minus 1. And we can do this by something a bit funny. So basically we do this cascade form. So we deal with this denominator part first. So we have 1 over 1 minus 1 over 4 z minus 1, then multiply with this 1 minus 1 over 2 z minus 1. And the first part, this is exactly same as this thing, so we can just put this part first here, okay? And we say x of n goes through this thing will become v of n. So that is v of n has, I guess, then we know big V will be, let me try to write. So what we mean here is that, so this thing goes to this part, become v of n, and in terms of the domain, then big V will be big X multiplied by the first part. Okay, so until here we have v of n. So maybe let's write here. So we have some big V or big V of z equal to this fraction part. 1 over 4 z minus 1 times big X over z. Okay, so this is what we want, and then we want to control other things that give us this 1 minus 2 z minus 1 on our big V. Okay, so we have some big V that already multiply with this fraction part, and our y we want to multiply with other thing. Okay, and then we kind of do the transform on this thing because we want to multiply with this extra 1 minus 2 z minus 1 factor. Then we kind of will go back to time domain and see what should happen. So we see that y of n should be have this one part become v of n, and you should be minus 2 times z minus 1 on your v of n. But we already know this z minus 1 in terms of time domain is just a time delay, so it's just this minus 1. And I guess it's a bit easier to, also it's a bit easier to just see everything in, maybe it's easier to see everything in z domain, right? So in z domain, then we have two other terms. So we have the original term 1, and we have minus 2 z minus 1. Okay. So what we can do is then we have this big V here, and then we have other signal that multiply with this minus 2 and z minus 1. Okay. And yeah, so from here then you see that this cascade form should work out, and your output y should, big Y should be big X multiplied by this factor, then this factor. Okay. And so that's the construction here. So we'll have our big Y equal to factor 1 times factor 2 big X. Okay. That's the construction, and we can simplify the construction a little bit by just looking at here, and we see we have 2z minus 1 here. And so if we want to save some component in our engineering, then we can combine this z minus 1, because those 2z minus 1 come from basically the same signal v of n. Okay. So we can just combine those 2z minus 1 to get this signal, to get this function, this this diagram instead. So this will be a little more economical. So we say we go through here, and this input we just go through the send Z-1, and then after we do Z-1, we split the signal into 2 copies, and one of them go to this 1/4, another one of them go to this -2. And so this more complicated feedback loop will give us all the system we want. Okay. And now from this, from here, then it's harder to see the intent of our construction, but anyway, it should be correct for giving our h of z. Okay, and yeah, so this is wording for saying that we can combine these two z-1. Okay, and we'll get this result. And next we have a higher order system that give us a more complicated block diagram. And once again, we can have 3 different forms kind of corresponding to 3 different ways to break up our system function. So here we have a second order system, that's second order in the denominator in terms of z-1. And so let's see the result clearly. So we have 3 different forms. We have a direct form and cascade form and parallel form. So for direct form is corresponding to looking at this thing as looking at this h of z as a difference equation. So we have h of z, you write as a difference equation. It is y plus 1/4 y over n minus 1. Then it is minus 1/8. Then the minus 2 y become y over n minus 2, etc. equal to x of n. And then I guess it is direct form. And then once again, you can write y of n as x of n y of n equal to x of n plus 2 different terms. Okay, so y of n will equal to, I guess I should write it here again, y of n equal to x of n and minus 1/4 y of minus 1 and plus 1/8 y of n minus 2. Okay. And that's exactly what this picture gives us. So y of n will equal to x of n plus the first line here. This is this minus 1/4, and z-1 give you this y over minus 1, and then you have plus 1/8, and this this z-1 on z-1 give you y over minus 2. So this is a direct form. Y of n equal to x over minus 1/4, the y over minus 1 plus 1/8 y over minus 2. And then we have the cascade form, kind of similar to what we have. So we cascade into these 2 factors. And yeah, so the first one should give you this 1/1 plus 1/2 z-1 factor. And then the second loop give you this 1/1 minus 1/4 z-1 factor. And then you can also do partial fraction expansion of h of z equal these 2 partial fractions, and each partial fraction have its feedback loop to give you this 1/1 minus a z-1 factor, etc. Okay, so those are the 3 forms of the block diagrams. Okay, so let's highlight a little bit. We have direct form and cascade form and parallel form. Okay. Okay, they corresponding to different way to break up our h of z, and finally we see that we can have more complicated h of z, and once again this so both upper and the lower case has non-zero powers. And once again, you can write it in multiple forms. And for direct form, you can combine. So I guess we don't skip the details, but for direct forms, you can combine some of the z-1. So the rate form is we write the rate form as the denominator term multiplying with the numerator term, and the denominator term was this part. Okay, so I guess let's do drawing and erase. Okay, so this first denominator term kind of corresponding to this part of the picture that we already see. And then the second part, you can separate them, but just like before, we want to reuse those z minus 1, and so you can just get this z minus 1 from this z minus 1. And so this z minus 1 go to this minus 7 over 4, that's this minus 7 over 4, and you also reuse this z minus 1 to become this z minus 1, to become this z minus 2, and then feed forward to this 1 over 2. And yeah, so this is a more complicated feature, and we basically reuse those 2z minus 1, but they give us a different result in, they give us two different purpose in this picture, because on the left hand side this is a feedback, so it's go back to with the, combine with this input, and because of this feedback it becomes this denominator term, and the other part actually become feed forward, so this part will combine with our input to become output, and yeah, so it combine with whatever give us yeah, it combine forward to become this output, and it becomes those numerator term. Okay. Yeah. Okay, and that's all I want to say about block diagram for Z transform. And let's try to talk about unilateral Z transform and use it to solve initial value problems. Okay. And so unilateral Z transform, just like unilateral Laplace transform, it's very similar to the bilateral part, but now the summations start from n equal to 0. So only care about this non-negative n. So we have this notation script x of z equal to summation n from 0 to infinity x of n z of minus n. And our shorthand notation is this. So everything is not harder to type, so we have a script big letter, script capitalized letter for everything. So the script x is a unilateral Z transform of our small x. So we write this double arrow uz as unilateral Z transform, and we also write it like this. So uz of x of n. And just like before, a very simple example is this exponential decay a of n u of n, and because this signal already starts from n equal to 0, so it's a unilateral and a bilateral transform are the same, because they only have n greater or equal part. And so the unilateral Z transform will be this 1 over 1 minus a z minus 1. Okay. And the RC we write it here, but the RC is actually not important, because because a unilateral Z transform is also always right-sided, so we always pick the rightmost RC. And the next example, we see what happens when our signal doesn't start from z equals 0. So we have the same signal, but time shift a little bit, so that it starts from n equal to minus 1. So we have a to n plus 1, u of n plus 1. So this started minus 1 equal to 1. Okay, and so we apply Z transform on this thing. Then it's very similar. It just applies. You have a time shift, so you get HRZ here. You have x of z equal to z over 1 minus a z minus 1. But if you do this unilateral Z transform summation, because you only sum from n equal to 0, you will not sum this 1. And so you do calculation, you see you have a over 1 minus a z minus 1 instead of z. Okay, so you see you have two different algebraic equations here, and the unilateral Lie transform is not equal to the bilateral Lie transform here. For the signal that start from n equal to -1. Okay. And as we said, so we consider unilateral Lie transform with this complicated expression of z -1, and then we try to we didn't specify RLC here, but now we think about, we want to know what is RLC, then we know that the RLC must be the almost 1, because the transform always correspond to a right-sided signal. So if this is a unilateral transform always correspond to a right-sided signal. So if this is a unilateral transform, then the RLC must be the almost RLC. So we don't need to specify RLC here. We already know the RLC must be the almost 1. And from here we can do the inverse Lie transform. So we can do partial fraction expansion with picking RLC being the almost RLC. Then we'll inverse Lie transform to this x of n equal to 1/4 to n u of n plus 2 times 1/3 to n u of n. And here something a bit important is we also set n greater equal to 0. Because unilateral Lie transform only care about n greater equal to 0, so when you invert back, you also only get the information on n greater equal to 0. Okay. And next one, there is something. Okay, the next one we talk about different way to do inverse Lie transform. Okay. For inverse Laplace transform, we say you can also expand in power series. And just look at the power series to do your inverse Laplace transform. For example, you have this signal. We can do similar thing for inverter to do inverse unit. Oh, sorry. This was a bilateral Lie transform. Okay, so sorry, I was saying different wrongness. Okay, so this is a way to do inverse bilateral Lie transform. And now for unilateral Lie transform, we can do similar inverse by having a power series method. But once again, we know our n only start from 0. So this power series here, n starts from 0. So this z to the -n must have 0 or negative power, or it has no positive power. Okay. And so if you want to do inverse unilateral Lie transform, then your power series must have no positive powers. Okay, so this is something important to remember. And so for example, this is consistent with this example. Our x of z is 1/1 minus az minus 1. And for different RLC, it will have different power series. And one of them have positive power, another one doesn't have. And we see that if we have the pick this outside RLC, then the power series will have only 0 or negative powers of z, and this is consistent with our analysis. Okay, so only this RLC has a unilateral Lie transform. And also something interesting happen here is that not every function of z is a unilateral Lie transform. Okay, so this is an important concept to remember. Okay, not everything is unilateral Lie transform, because we know if unilateral Lie transform, then you also always have then as a power series, you always have non-positive powers of z. Okay, so if your function cannot be expressed as this non-positive power of z, then it's not a unilateral Lie transform. And for example, if you are a rational function, then this no positive power means that no positive power will means that the degree of a numerator must be no bigger than degree of the denominator. I guess I should write the n and the p here. Okay, so numerator of z and denominator of z. Okay, and that's because basically, okay, so basically the reason here is that h of z basically corresponds to x of n, that's causal. Okay. And we know x of n is causal, then h of z need to be finite as z goes to infinity. The infinity must be inside RC. The causality property we start today. Okay, and so h of z need to be finite as z goes to infinity. So n of z must not have a power degree more than this d of z. And for example, example just see. So this time advance signal. So x of n equal to a to the n minus 1 u of n. We know is z transform is this bilateral z transform is z over 1 minus a z minus 1. Is RC being outside. Okay, and so we write this as a rational function of z. It will be z cubed, z squared over z minus a, and we see that this is this polynomial go to infinity as z go to infinity, and so this cannot be expressed as a power series that only have non-positive power. Okay. And so this this rational polynomial, this rational function of z cannot be a unilateral. This rational function of z cannot be a unilateral z transform. Okay, even if you pick the outside RC. Okay, that's because if you pick outside RC, but you don't have infinity inside your RC. Then you inverse z transform, then you only get a right-sided signal. So this is a right-sided signal, but it's not a causal signal. Okay. You want to be 0 for all z less than 0. Okay, and yeah. So the signal doesn't corresponding to unilateral z transform. Okay, if I'm okay with this concept. Only nice signals that including infinity inside RC has inverse z transform. Okay, and then we go to property of z transform, but we actually skip most of them, and we say we'll put a table 10.3 to summarize them, but I think actually we forgot to put the adding slide, so I will update the slide later. Okay, so we should have a table 10.3. But most of them are similar to the bilateral z transform. So for example, we have a convolution and we have multiplication on the other side. But for now, we basically need to have everything in this associated to causal. Okay. So we want x1 of n equal to x2 of n equal 0 for n less than 0, etc. Okay, and let's see. Let's skip this example because it's a little annoying. Then let's talk about, go straight into what we want. So we want to solve a difference equation. And to solve difference equation, what we need is this time shifting property. Okay, so we need to see what happens when y equal to x over n minus 1, y of n equal to x over n minus 1, what's the unilateral transform of y. Okay, and this is a bit tricky, but we can anyway derive something. Okay, so script y of n we run by definition is the summation n from 0 to infinity, x of n minus 1, z of minus n. And so this n equal to 0 term will give us x of minus 1, then plus n from 1 to infinity, x of n minus 1, z minus n. Then we can do a change of variable here. This is n from 0 to infinity. So we change n minus 1 to n. And so this new n will be from 0 to infinity, and every n minus 1 become n, and n become n plus 1. Okay. And then this term, we can just get, okay, so this is what we get so far. And then this HR, then we see that this is already very close to the unit, this second term is already very close to the unilateral Z transform of x of n, but we just have HR plus 1 here, and we can just get rid of that by writing HR Z minus 1 here. So we have HR Z minus 1 factor here. Okay, so we derive that the unilateral Z transform of this time delay signal x of n minus 1 is x of minus 1 plus z minus 1 times x of z. And it's a bit funny because we keep saying you only care about causal signal, but we have x of minus 1 here. But we will see that makes sense. This makes sense. We talk about solving initial value condition, initial value quotient for difference equation. Okay. I guess a bit of a thing here, because when we talk about initial values, we actually go to a bit of negative value. For example, when we talk about initial race condition for difference equation, so here is a small reminder. When we talk about initial race condition, we say x of 0 for n less than n0. Then we say our y needs to be 0 for big N different values, that's before n0. Okay, so we talk about initial value for difference equation. Because of how things structured, we always think about going back a little bit before this initial value, this start of time. Okay, so that's kind of justify why we can write x of minus 1 here, even though this is kind of HR information for your unilateral Z transform. The second part only depends on the unilateral Z transform of x, but here you go out a little bit to get x of minus 1. Okay, and so this is basically the equation we use to solve the initial value problem for our difference equation. And if we want to have a higher order term, then we need to use this equation twice. So we think about some w of n equal to y of n minus 1, which is equal to x of n minus 2. Then we see that unilateral Z transform of w will equal to apply this on we apply this thing on y, and it will become x of minus 2 plus x of minus 1 z minus 1 plus a squared script x, script big X. Okay, so this is similar to what we do in Laplace transform for our differential differentiation property. So skip that. And also we have more general terms. So more generals, if you want x over n minus k, then you will have x over minus k term, x over k minus k plus 1 term, etc. all the way to this script x term. Okay, so this is a time delay property, and also in one of the textbook problem, you can derive the time advance property, and you get this result. So you have this square x part that you see that's exactly invert of this y of z, but then you have this HR boundary term, so minus dx of 0. Okay, and finally we have 20 minutes, and let's try to solve difference equation with the initial condition. Okay, so we have our first order difference equation. I guess we are left with a bit too much time. But anyway, we have our first order difference equation. Y of n plus 3y of n minus 1 equal to x of n. Okay, and and we have So this is our equation, and then we have our x of n equal to alpha u of n. This is quite a simple input, and we have initial condition. And as we say, initial condition actually happen before t equal to 0. Initial condition is y of -1 equal to beta. And so we'll apply unilateral transform on both sides. And okay, and use the linearity and this time delay property. We get so y of n will unilateral transform to just square big Y, and then it's 3y of n-1. So y of n-1 we use this become y of y at -1. So y at -1 is just this beta. So this is 3 beta, and z-1 times script y. So we have z-1 script y, and then times these 3. And the other side, x of n is alpha times u of n, and u of n will is a right-sided signal. Sorry, it's a causal signal, and it will just a unilateral Z-transform, same as bilateral Z-transform is 1 over 1 minus Z-1, and we have alpha go to this alpha. And now we can try to solve y of z by grouping things together to see what's script y. So script y will be equal to, so there are different terms. So first there are terms that are linear to this beta. So it's 3 beta divided by this minus, so minus 3 beta, because you move 3 beta to the other side, and divide by this 1 plus 3z minus 1, okay? Because you have a 1 here and a 3z minus 1 here. So minus 3 beta divided by 1 plus 3z minus 1. And also this alpha over 1 minus z minus 1 term, then divide by another 1 plus 3z minus 1. Okay, and so this is just like the initial value problem for Laplace transform. So here we have two different terms. So we have the zero input response. So this beta term is the response when alpha equal to 0. So it's a 0 input because the input is x of n. Okay, and then we also have this 0 state response, means this is a response when the initial condition or initial state is 0, and the initial state is this beta here. So once again, we see that the response to initial value problem is a linear combination of zero input response and zero state response. And this is a bit of funny notation, because zero input response corresponding to response to initial state, and zero state response correspond to the response to the input. Okay. Anyway, so this is funny name, but if we give actual value for this beta and alpha, then we can write down our if we have actual value of beta and alpha, then we can solve the y of n as a time domain. So for example, we have some alpha equal to 8 and beta equal to 1. Then we have our y of z now as a rational function of z minus 1. And we can do partial fraction expansion or not so total expansion. But anyway, we get some partial fraction of this z minus 1. And then we can do inverse unilateral Z transform. Basically by doing the inverse bilateral Z transform, picking out z being outside. And we see that y of n will equal to this 3 times the a equal to minus 3 here, so minus 3 to n, plus 2, and with a equal to 1 here, and u of n. And so y of n equal to this for n greater or equal to 0. Okay, and this is initial value problems from starting from n equal to 0. So yeah, initial value problems are from n equal to 0, and so we don't really know what y for n less than 0. I guess except for the initial value, we have an initial value of y at minus 1 here. Okay, so I guess that's all we want to talk about in this class. And it's a bit faster than my expectation, but it's okay. And so now we finish the transform, and on Thursday, as we said, we will have a review for final, and next Monday we'll have our final. So if you have no question, then see you on Thursday, and hopefully you are doing well on your final. Okay, and we can take a break now.